Hello, this is Dr. Baxley, and this is the video lecture for Chapter 6, Thermochemistry. This is Part 1, all about energy and the first law of thermodynamics. It'll be really helpful to have your printable lecture notes available to go along with this particular lecture. Before we get into chemistry, it'll be really helpful to know some things about energy. One type of energy is potential energy. That's the energy of position. As you can see in the diagram below, if a person is holding a ball above a table, there's the potential for that ball to drop towards the table. It's being pulled down towards the table due to gravity. So it has some potential energy as those two objects, the ball and the table, are rearranged in terms of position. There's a formula for potential energy here, and it relates to the mass of an object, the height of an object, and the gravitational pull of an object for gravitational potential energy. Another type of energy is kinetic energy, or the energy of motion. The energy of motion can be calculated with mass times velocity, as shown in the formula. And this is also shown in the picture on the screen, where the person has let go of the ball. It is now moving towards the tabletop, and the ball now has some kinetic energy because it has a mass and it has a velocity going down towards the table. Energy can be converted to different forms. For example, potential energy can get converted to kinetic energy, or kinetic energy can get converted to chemical energy. This can be seen in the diagram below too. The person can pick up the ball off the table, giving it the potential to rearrange in terms of position. Dropping the ball gives the ball some kinetic energy as it starts falling and moving. So all those different energies can be converted from one form to another. If you ever think energy is missing in a system, that missing energy is usually lost as heat, or thermal energy to the surrounding. For example, once the ball hits the table, it's no longer moving, it no longer has as much potential energy as it used to, and it doesn't have as much kinetic energy because it's not moving anymore. But that ball still has the amount of energy it used to have. That ball just happens to have a bunch of energy tied up in thermal energy as the ball gets warmer as it collides with the table. There's a handy flowchart in your text about kinetic and potential energy. Kinetic energy is on the left, and kinetic energy, due to motion, is also related to temperature because temperature is associated with particles that are moving. The faster the particles wiggle and jiggle, the more kinetic energy they have, and the higher the temperature of that substance. On the right side of the diagram is potential energy. Potential energy is due to position in terms of things like gravity and the balls, as we saw in the previous figure, but it's also due to the composition of chemicals in terms of the position of atoms and ions in chemical reactions. So potential energy is most closely related to chemical energy in terms of where those atoms are in reactants and where atoms are in the products. The law of conservation of energy says that energy can't be created or destroyed. It can only be transferred or converted to different forms. This is the first law of thermodynamics, and it's a law that has no apparent violations. There are certain attractive forces that we'll need to worry about in chemistry. In general, energy is released when two objects with attractive forces are allowed to come together. The fundamental attractive forces that we have in nature are gravity and electromagnetic forces, and the strong nuclear force. Now we all know about gravity because things fall when we drop them. The electromagnetic forces are things like Thomas the Train sets, where the magnets can pull Annabelle and Clarabelle close together. The strong nuclear force is exactly that. It's really strong, and it's in the nucleus of atoms. It's super, super strong, like millions of times stronger than the force of gravity. We don't see it in day-to-day life because it's only exerted in the nuclei of atoms. We've talked about how potential energy can be converted to kinetic energy when the positions of objects are rearranged. The same is true for chemical reactions, where chemical energy is exchanged with potential or kinetic energy when positions of atoms or ions are rearranged. For example, hydrogen atoms that are far apart in space can rearrange, become closer together, and they can then form a molecule of H2. That mere rearrangement in space of the two atoms allows a bond to form and energy to be released. Here's a concept question for you. Chemical energy is released when chemical bonds are broken. It's either true or false. Pause the video, think for a moment, and decide which your answer is. Is chemical energy released when chemical bonds are broken? It turns out this is false. In order to separate any object that has an attractive force with another object, one has to put energy into that system. For example, to lift up the ball in the previous picture, you would have to put energy into the system. The ball would have to absorb some energy from you. In order to separate the two atoms of hydrogen from each other, they would have to be pulled apart and separated. Energy would have to go into the system. Energy is always released when chemical bonds form, and energy is always absorbed when chemical bonds are broken. Chemical bonds are not like light sticks or eggs. When you crack them open, the energy comes out. This is kind of a biology model of energy, where biologists in biology books will often show students that ATP turns into ADP plus energy. This is where lots of people get the egg model of energy, where the energy just falls out when bonds are broken. What really happens is that water has to react with ATP, and ADP forms along with some hydrogen phosphate. Forming those new substances is what releases energy when bonds are formed. We'll talk a moment about units of energy. The SI unit for energy is joules, named after an old dead English guy named Joule. A joule isn't very much energy. It takes 80,000 joules to heat up a cup of water from 20 degrees Celsius to 100 degrees Celsius. There were old units of energy before joules. The old unit was the calorie. You might be familiar with that one. A calorie was defined as how much heat it was required to warm a gram of water by 1 degree Celsius. A gram of water is not very much. It might be 20 drops of water. A degree Celsius is not very much. You can't almost even tell the difference between a 21 degree Celsius cup of water and a 22 degree cup of water. In terms of calories and joules, a calorie is 4.184 joules, and that's an exact conversion. Now, a nutritional or food calorie is often spelled, or usually spelled, with a capital C. A food calorie is worth 1,000 chemist calories, or 1 kcal. So if you look at a Snickers bar and you see that it has 240 calories, it really has 240,000 chemistry calories. But of course the Snickers bar people aren't going to put that on their Snickers bar, because who's going to eat a Snickers bar that had 240,000 calories? It would take a long time in the gym to work that off. Well, you'd have to do your gym exercises in terms of chemist calories per hour too, and you'd be easily getting like 600,000 calories per hour if you were working out pretty hard. Let's spend a few minutes on energy. Energy is hard to define, but one definition is that it's the ability to make things change. Work can be classified as energy in terms of mechanical work like pushing an object, or pressure volume work, the PV, for gases when gases are expanding into a system. Total internal energy is also something that can change. That is the rotation, bending, and wiggling and jiggling of atoms or molecules in a larger substance. Heat is something that energy can make change, and that is to transfer thermal energy between objects. For example, moving energy between a hot object to a cold object. Temperature is related to the internal energy of an object. So the more rotation, bending, twisting, stretching, wiggling and jiggling of atoms and molecules in a particular substance, that all adds up to what we consider temperature, or how much internal energy it has. In terms of chemistry, there are two things energy changes in chemical reactions can do. One thing is to change the total internal energy, either to make a substance hotter or colder. Another thing a chemical reaction can do is to change the pressure volume and do some work. We can see lots of examples of both changing internal energy and pressure volume work in our day-to-day lives. Here's a fancy setup where there's some zinc metal that's put into a flask that's sealed up at the top. There's a movable piston at the top. As the zinc metal goes into the HCl, the reaction is going to create some H2 gas, like you saw in the chemical reactions lab. Here's what happens afterwards. The zinc is now in the flask. There's lots of bubbles of H2 gas forming. Because the container was sealed, the pressure increase by adding more gas molecules to the system has caused the piston to move up. This is what's known as pressure volume work, because either the pressure goes up or the volume of the system goes up. This is exactly how internal combustion engines work. There's a large volume change and pressure change inside the cylinder of the car, and it pushes the cylinder up, which eventually turns into mechanical energy to make your car drive. The first law of thermo, as we saw before, says that energy can't be created or destroyed. In mathematical terms, that means the change in energy in a particular system is going to be equal to the change in energy of the system plus the change in energy of surroundings. And all that has to add up to 0 because energy can't be created or destroyed. If we rearrange that just a little bit, you can see that the energy of the system, how it changes, is going to be equal to the negative value of the energy of the surroundings, just by subtracting E surroundings from both sides of that equation. So if the energy coming out of a system is equal to the energy going into the surroundings, where does all of our energy come from that we use on our planet? Well, fortunately, there's a great big ball of glowing gas in the sky that provides all the energy we need in terms of solar energy. Almost everything driven on the Earth in terms of energy is driven by the sun and all the energy it radiates. Here's a nice little schematic that shows what happens with energy flow to the system and the surroundings. So if energy is moving from a system to the surroundings, the change in energy for the system is going to be less than 0 or negative. Imagine that the energy flow is like money flow. So if the system started with $10 and some energy flowed out of it, it would end up maybe being $5. And so its change in money is negative. The surroundings would then have to go up by $5. Its change in energy is positive. In terms of chemical reactions, the energy of a system will go up or down depending on that rearrangement of particles. So in this particular figure, carbon's reacting with oxygen to form CO2. CO2 just happens to be lower in energy overall than the reactants in their positions. And so energy is being released from the reactants, and it would go into the surroundings. This is the end of part 1 of the video lecture for chapter 6. Come back and look at the next sections. We'll talk about state functions, enthalpy, chemical reactions, and energy in the United States.